Hello everyone. Today let's talk about the Abelian group. Here is the definition of Abelian group. We can see that Abelian group is the group if we consider the group is G with the operation star, then we can call it Abelian, or sometimes people call it commutative. When for any two elements A and B in G, they have the property that if we do the operation like A star B, then it is equal to B star A. So it means you can switch the order of the two elements when you do the operation, but the result of those two orders will be the same. And the Abelian group is a very important group because a lot of groups has the Abelian property. So we can look at some examples. For example, first we can look at this group, the group of integers under the addition operation. So for example, 5 plus 120, 5 and 120 are the integers. We get the result is 125, and 125 is equal to 120 plus 5. So you can see at the left hand side we do the addition, like we put 5 at the first and 120 to the second place, and on the right hand side the 120 is on the left position and the 5 is on the right position, but no matter how we change the order like this, both of them have the same result, 125. And this is true for any integers when we do the addition. So this means this group integers under addition is an Abelian group. Okay, another similar group is the real numbers exclude the zero under the multiplication. Here this notation is, we know this R, the big R is the set of all real numbers, but if we put like a cross symbol to its power, it means the R, but all the integers, all the real numbers, but we exclude the zero from this set. Okay, so for this group, it is Abelian because, for example, square root 2 is not 0, and it is a real number, and we multiply it with, for example, pi. Pi is also a non-zero real number, and it is equal to pi times square root 2. So this, it means those two numbers can be commuted when you do the multiplication, and this is also true for any other numbers in the real numbers. So it means this group is Abelian. And there is a very very commonly used counterexample, that is matrix. If you learned about matrix or linear algebra, you will know that matrix or generally matrix usually does not commute when you do multiplication, the matrix multiplication. So if we look at this group, GLNR, this group is called a general linear group. It is defined as the elements in like n by n matrix over the real numbers, and the determinant of the matrix is not 0. In other words, the matrix is invertible. You can have an inverse of this matrix. So this group, if we only consider the elements of this group, it is a subset of all the matrix. So this group is actually not Abelian. That is because we can take a example to show that if we consider A is a matrix in like 2 by 2, like a GL2, which is a 2 by 2 matrix, which the determinant is not 0, and we consider this matrix, this 2 by 2 matrix, and B is equal to another 2 by 2 matrix like this. We can first check A and B are elements of this GLN. That is, the determinant of A is 2 times 1 minus 0 times 1 equals 2. So this is not equal to 0, which means A is in GL2R, right? And the determinant of B equals to 1 times 0 minus 3 times 1 equals to 3, which is also not 0. So B is also an element of GL2R. Okay. So now we consider the matrix multiplication between A and B. That is, we first consider A times B. This equals to 3, 6, 1, 0. And if we do the opposite order, B times A, that is 2, 4, 2, 1. Obviously, A times B does not equal to B times A, so we can conclude GL2R is not Abelian. Okay, so here we can see that to prove a group is not Abelian, we just need to find one counterexample, just like this, to show like there are 2 elements in this group that does not follow the commutative property. Then we can see this group is not Abelian. But if we want to prove that the group is Abelian, like those 2, we need to check every 2 elements in the group and show that they are commutative. So that is how you can prove the Abelian property of a group if you just follow the definition to prove it. Okay, that is the Abelian group, and we will use the Abelian group very often in the future. So this is a very important group. So that's all I want to talk today. So see you next time.